NCCER 34108-10 Welding Basics, Boilermaking Level 1, 2.0 Welding and Cutting Processes. Gary A. Pace, PE, CWI, May 2019. Okay, let's just start with oxygen is not our friend. If we're starting out in welding, the first thing I tell any students I've ever had is oxygen is not our friend. Yeah, I know we're breathing it and you can go that direction, but the whole basis of welding in Earth's atmosphere is to avoid having oxygen and nitrogen contaminate your weld pool, the liquid weld metal. Iron, steels, and most other metals are not really good with having oxygen in the weld pool. So I always first thing I tell students is oxygen is not our friend. Metals at high temperatures are reactive chemically with the main constituents of air, oxygen and nitrogen. Should the metal in the molten weld pool come in contact with air, porosity, oxides, and nitrides would be formed, which upon solidification of the molten pool could destroy the strength properties of the weld joint. So we want to keep these guys out of our weld pool, out of our weld joint. Nitrogen and oxygen. That's pretty much the whole game for welding, is keeping these things out, whether we're using a shielding gas, whether you're using a flux and it forms a slag, or we're welding in a vacuum chamber. This is the game. This is the whole purpose of welding, is to keep oxygen from contaminating our weld pool. What is arc welding? The definition of arc welding: it's a group of welding processes producing coalescence of workpieces by melting them with an arc. The processes are used with or without the application of pressure and with or without filler metal. In the arc welding process, the weld is produced by the extreme heat of an electric arc drawn between an electrode and the workpiece, or in some cases between two electrodes. A localized fusion of metals produced by the heating to suitable temperatures. The filler metal has a melting point approximately the same or below the base metal, but always above 800 degrees F, 427 degrees C. So it's telling us that we actually have to melt the base metal. That's the difference between welding and brazing, or welding and soldering. Soldering and brazing, you don't melt the base metal. You just put a brazed material or a soldering material. That metal melts and it sticks to the base material by capillary action, etc. We're not going to get into that. But in brazing and soldering, you don't actually melt the base material. In welding, we melt the base material, and it's got to be above 800 degrees F for it to be considered arc welding, or welding, period. 2.1 Shielded Metal Arc Welding, SMAW. So we're going to cover a few slides. We're going to talk about stick welding, shielded metal arc welding. I'm sure everybody's seen this in somebody's garage or on the work site. So basically what we've got here is a piece of wire, and it's covered by a covering. It's covered by what we call a flux, a covering. That is going to decompose in the electric arc when we strike an arc, and it's going to produce a shielding atmosphere and a slag. And these are going to help protect our molten weld metal from our not friend oxygen. Remember, we were trying to keep nitrogen and oxygen out of the weld pool? Well, that's why we've got this electrode covering. So the first electrode coverings back in the day were made of cellulose, basically wood chips and paper. If you look up E6010, in a later module we'll talk about some electrode coverings, but E6010 is one of the first electrodes, and it has a cellulose covering because somebody figured out that, hey, if we burn wood chips and paper on the outside of this electrode, it's going to help us deposit better weld metal. We're not going to have porosity and cracking and a lot of impurities or atmospheric contamination in our weld metal. So that was one of the first electrodes. So that's why when we have shielded metal arc welding, you're going to see there's a covering on the outside of the electrode. And there's a whole bunch of different kinds, different specifications, but that's the basics of this process. You basically have a wire, a piece of coat hanger, and it's covered with either a flux that's made of wood chips and paper, or it can be made of a mineral coating, limestones and all kinds of different formulations of these mineral coatings on the electrode covering. Principles of SMAW. The electric arc produces heat that heats the base metal to its melting temperature. As the flux covering on the electrode wire melts, a shielding gas is created. When the flux cools, it solidifies and forms a protective slag over the weld bead. As the electrode wire melts, it becomes the filler metal to the weld. So we strike an arc, it produces heat, it melts the electrode, but it also decomposes or burns up our electrode covering, our flux, and that gives off a slag, and it also kicks off a shielding gas that protects our molten weld pool from atmospheric contamination. And here you can see a handful of different filler metals, electrodes that are used in shielded metal arc welding, often called stick welding, but these are some electrodes, but that's the basic principles of shielded metal arc welding. Shielded metal arc welding is the most common form of welding. An arc welding machine supplies the electric current to the electrode wire. The electric current travels through the air gap between the end of the electrode wire and the base metal. As the electric current flows through the air gap, an electric arc is formed.
Several basic devices are needed to make a manual arc weld. They are the power source, welding cables, electrode holder, ground connection, and electrode. The power source provides the electrical energy to melt the workpiece and the electrode. The power source must permit control of the arc characteristics as required for a specific job. The welding cables connect the electrode holder and ground clamp to the power source. The cable carries the electrical current from the power source through the arc to the base metal being welded. The ground cable connects the power source with the workpiece, thus completing the electrical circuit. The ground connection must be good to prevent arc blow. The electrode holder is merely a clamping device for grasping the electrode. The electrode is part of the electrical circuit and it is consumed during the welding process. It fills the joint and thereby becomes a part of the weld. This slide you can see a couple of examples of shielded metal arc welding electrode holders. The bottom left hand corner you can see some examples of shielded metal arc welding electrodes, and you take the electrode, you put it in the holder and strike an arc, and the picture you see there with the individual making a fillet weld there, that's what shielded metal arc welding is all about. Using an electrode to deposit sound weld metal into a weld joint.
The gas-producing materials in the coating give out lots of gases due to dissociation and combustion. The gases produced form a protective gas shield around the arc. This helps shielding the arc and the weld metal from atmospheric oxygen, hydrogen, and nitrogen. So once again, it gets back to we just want to shield the liquid weld metal from oxygen, hydrogen, nitrogen, keep them from getting contaminated. It gets back to oxygen's not our friend. It's a fancy way of, or a poor man's way of saying we're trying to avoid atmospheric contamination. Advantages of shielded metal arc welding. The equipment is inexpensive. Equipment is portable. Applications are simple and adaptable to job requirements, and it can be used with several types of filler metals. So you can use this with steel, stainless steels, nickel alloys. There's a lot of different processes. And it's portable. If you want to go and weld in the wind of West Texas, or if you're outside in the winter in North Dakota or something, this is a pretty good process. You might have to cover up some things, but this process is pretty good. This picture of this gentleman, I think he's welding under a bridge somewhere, which you might not be able to do with a lot of other processes. And you're able to deposit sound weld metal on a pretty consistent basis in a lot of different applications: boilers, pressure vessels, piping. You can make X-ray quality welds with this, with the right kind of personnel making the welds. Disadvantages of shielded metal arc welding: requires slag removal. There's also harmful gases that can be produced when the flux melts, especially when you're doing stuff with a lot of nickel alloys or stainless steel alloys with chromium and hexavalent chrome, and there's some things that can go on there with the smoke and the fumes. Changing the electrodes can slow down the process. Well, this is pretty obvious. It's not an automated process, which leads to low deposition rates. And it also, you can't automate it like shielded or gas metal arc welding or Flux-Cored arc welding or submerged arc welding, even gas tungsten arc welding. A lot of times you can automate the process. Here you can't really automate this process just because you have to change out the electrodes. So that's one of the some of the disadvantages of shielded metal arc welding. Gas tungsten arc welding, GTAW, aka TIG welding. Okay, here we're going to use a non-consumable tungsten electrode. So instead of like shielded metal arc welding where our electrode becomes part of the weld, here we use a piece of tungsten. It can be performed with or without filler metal. We're going to need a shielding gas. It can be manual, semi-automatic, or automatic. It's applicable to several boilermaker applications. It's widely used in orbital welding and in overlays. So this process, like I said, uses tungsten, the T in there. This is the only time you're going to see tungsten as an electrode. GTAW background. GTAW welding uses non-consumable tungsten electrode. Filler metal, when required, is added by hand, and you use a shielding gas to protect the weld and the tungsten. Once again, it gets back to oxygen's not our friend. So in this instance, we're going to use either argon or helium to protect our weld metal and our tungsten from atmospheric contamination, which would be oxygen, nitrogen, hydrogen, and whatever else is out there lurking to destroy our weld or wreak havoc on it. But the key here is non-consumable. So we run electricity through our tungsten electrode, and then it causes an arc, and then it causes melting of the base metal. We get a weld puddle there. We've got a shielding gas flowing over that, keeping the oxygen and nitrogen from contaminating it. And if we need filler metal added, we're going to use basically a straightened out coat hanger, and we're just going to add wire into our weld puddle and melt it manually. In the gas tungsten arc welding GTAW process, the arc is established between the tip of the tungsten electrode and the workpiece to melt the base metal and filler metal if filler metal is used. Because of its extremely high melting temperature, tungsten electrode is considered to be non-consumable. Tungsten's melting point is 6,191 degrees Fahrenheit. Steel melts, we'll call it 2,800, somewhere in there, 2,600 to 3,000 in that ball game, depending on what you've got going on. So you can see we've got 3,000 degrees to play with from the melting point of steel to the melting point of tungsten. An inert shielding gas protects the molten weld pool and the non-consumable tungsten electrode. The process is often referred to as TIG, short for tungsten inert gas. You might also hear the terminology heliarc. These are old terms. You'll still hear TIG today. It's just, it's there, it's stuck. But for technical conversations, you use GTAW. That's the American Welding Society's preferred acronym, GTAW. But if you use TIG, you're not going to get laughed out of the place. TIG flows a little better than GTAW does. So for conversations, it's not going to kill you to use the word TIG or HeliArc. HeliArc takes you back to the 60s and the old guy times. Here you can see we've got a GTAW torch in the process. We're adding filler rod to our weld puddle down there. The filler rod doesn't have any electrode flowing through it. It's just a rod. Our tungsten is the electrode. That's where the electricity is coming from. That's the difference. One of the main differences between this process and other processes is here we have a non-consumable tungsten electrode. Most other processes are filler material. We run electricity through it to get it to melt. Here we add our filler material, our rod, into the weld puddle and it melts then. There's no electricity running through the filler rod. Here we got a couple of TIG torches. One's the process side of it, so you can see, how this thing goes together. And the other one's just a picture showing you a manual gas tungsten arc welding torch or a TIG torch that's used in, industry. These things, if you're around welding very long, you're going to come across this process. Here we've got the electrodes. We color code the electrodes, not we, but I guess we, the welding industry, color codes the electrodes to make sure that you're using the right electrode. There's different alloying elements they put into the tungsten to get different electrical characteristics for different metals and to get the electricity to flow through them different. So you can see that at the top, so we got like red, gray, yellow, green. There's different paint colors that correspond to a recipe, I would say, or an alloy of tungsten where they put thorium, cerium, or other metals into the tungsten to get an electrode with a very specific set of electrical characteristics. So that's what the tungsten electrodes look like. Gas tungsten arc welding advantages. It welds more metals and metal alloys than any other process. High quality and precision, pinpoint control, aesthetic weld beads, no sparks or spatter, no flux or slag, and no smoke or fumes. So there's a lot of different things you can do with TIG welding, gas tungsten arc welding. It's a really good process if you know how to use it. It's like using a scalpel to do something. So pretty solid process to use. Disadvantages. Like anything in life, you got advantages and disadvantages. So for gas tungsten arc welding disadvantages, we have lower filler metal deposition rates. You can't really, if you need to really build something big, if you're welding a 4-inch piece of carbon steel or something like that, it would take you forever to do it with gas tungsten arc welding. So it's generally used for, precision type applications and cleanliness. You got to have good hand-eye coordination skills. This is not something you're going to turn over to the new guys. Maybe they pick it up, maybe not, but this is not a welding process that is for the rookies. Brighter UV rays than other processes. We don't have a slag there to kind of soak up some of the UV radiation, so consequently it's easier to get a sunburn or a flash burn from this welding process. Slower travel speeds than other processes. That gets back to our deposition rates. Equipment costs tend to be higher than other processes because you need the electronics involved in TIG welding, gas tungsten arc welding, power supplies generally have some higher grade electronics in there because you have pulses and they have a lot of different what am I trying to say? Things that they can do to your electricity while it's flowing to get it to give you the characteristics you want to deposit sound weld metal. Gas metal arc welding, GMAW, and Flux-Cored arc welding, FCAW. These are two processes, depending on where you're at. It's two processes or one process, depending on which codes you're working to, but that's kind of outside the scope of what we got going on here. Basically, these are wire-fed processes. We got a spool of wire, and with gas metal arc welding, we just use, we're basically running a piece of wire. You know, think of going to the hardware store and getting a spool of wire, and you're going to run that through a set of rollers, and it's going to shoot that wire down a gun or down a cable through into the gun. We're going to run some electricity through it, and that wire is going to melt. And then we're going to use a shielding gas, usually carbon dioxide, argon, or hydrogen or helium, to protect our weld puddle, once again, from our not friend oxygen. Once again, we're trying to keep things from getting contaminated. So the difference between gas metal arc welding and Flux-Cored arc welding is Flux-Cored arc welding, we've got a flux on the inside of the wire. Remember we talked about a flux when we were talking about shielded metal arc welding? Well, instead of having the flux on the outside, now we've got the flux on the inside. Instead of it being glued to the outside of the wire, now we've basically made our own roll your own kind of cigarette, and we've put the flux on the inside of the wire. And they basically use the same equipment pretty much. You're going to have some different settings depending on what the wire is. And they can both use a shielding gas. Sometimes we've got what's called a dual shield, or a gas shielded Flux-Core, where we've got a flux and a gas. And sometimes you just have self-shielded with the Flux-Core. GMAW definition. Gas metal arc welding is a semi-automatic or automatic arc welding process in which a continuous and consumable wire electrode and shielding gas are delivered to the weld through a welding gun. GMAW can be carried out using a solid wire, metal cord, or a copper-coated solid wire electrode. The shielding gas or gas mixture may consist of the following: argon, carbon dioxide, argon and carbon dioxide, or argon mixtures with oxygen or helium mixtures. Each gas or gas mixture has a specific advantage and limitations. So we're not going to get hung up right now on the shielding gases, but we'll touch base on those after a bit. But here you can see the basis of the process. We're going to use a wire. We're going to run it down through a gun. It's going to contact. We're going to put some electricity through it. The electricity is going to cause our electrode to melt, and then we're going to end up with a molten weld puddle, and we're going to shield that with a shielding gas. We're going to keep the atmospheric contamination from happening by shielding that weld puddle with a shielding gas, usually argon, CO2, or mixtures of these gases. GMAW, commonly referred to as metal inert gas, MIG, welding, embraces a group of arc welding processes in which a continuous electrode, the wire, is fed by powered feed rolls, a wire feeder, into the weld pool. An electric arc is created between the tip of the wire and the weld pool. The wire is progressively melted at the same speed at which it is being fed and forms part of the weld pool. Both the arc and the weld pool are protected from atmospheric contamination by a shield of inert, non-reactive gas, which is delivered through a nozzle that is concentric with the welding wire guide tube. So that's telling us that we're feeding wire into in through the gun. We got electricity, and we're using a shielding gas to protect our weld puddle. I'm going to go from the left to the right here. So we've got our gas-powered welder generator. This would be for a situation where we're welding outside, probably not in a building type situation. You've got a a solid state wire feeder. So there's our wire feeder, and we'd plug our gun into it, which is the third from the left. You can see that semi-automatic weld gun. And then you can see on the far right, we've got a picture of what it would look like, our equipment would look like if it was in a shop type situation. This is one of the configurations. There's a lot of different configurations that you can have. A lot of modern technology, a lot of these power supplies are getting smaller and smaller and more streamlined, but you get the basic gist of what we've got going on here for gas metal arc welding equipment. Advantages of gas metal arc welding: low cost equipment, easily automated, low cost consumables, high deposition rates, good looking weld beads, aesthetic weld beads. You can get a low hydrogen deposit with this weld process. No flux or slag, which saves on cleaning. Low levels of spatter. You can weld almost any metals with it, and it's easy to learn. You can learn this welding process in a matter of days. It's pretty easy to get going on this. This is much easier welding process to learn than other processes. So that's one of the advantages. If you need welders and you can get it so you can weld using this process, a lot of times you can cure your manpower issues, your shortage issues with utilizing this welding process. One of the huge advantages of using gas metal arc welding is no slag removal. This is one of the great advantages of this process. So if you have to paint something or do some kind of processing, you don't have to worry about removing slag from it. Disadvantages of gas metal arc welding: it's sensitive to contaminants. Meaning that if you're outside in the rain or whatever, or if you're welding over dirty steel, this is not the process to use. There's some of the shielded metal arc welding electrodes are a little more forgiving when you're welding over things like mill scale or dirt or paint or rust or whatever's on the metal. Not that I'm suggesting doing that, but gas metal arc welding is very sensitive to contamination. Paint, oil, grease, there's all kinds of things that can give you problems with gas metal arc welding. Portability, not very portable. You can set it up to be somewhat portable, but you're not taking this thing 50 feet up in the air or snaking it back into some kind of crevice like you would be able to with gas metal or shielded metal arc welding. Lack of fusion. There's different transfer modes. We didn't talk about them here, but you can end up with welds that look very good, but they have a flaw in them called lack of fusion. So that's one of the problems with this process. Sensitive to wind. Used to work at a place in Iowa, and the end of the spring they'd open up the doors kind of because it'd start getting warm in the building. And we'd have all kinds of problems with our welds that were done with gas metal arc welding. It's an open arc process, so you get harmful UV rays also. The UV rays, because there's no slag over the weld puddle and the arc, so you're going to have more UV rays coming into contact with human beings. Hopefully not, but it's something that you need to deal with or work around. Flux-Cored arc welding, FCAW. These are, there's two variations of Flux-Cored arc welding. We've got gas shielded Flux-Core arc welding. This is generally for structural welding, and it's outside where we're not really worried about, where we're maybe worried about our shielding gas getting blown away or a situation like that. And then we've got self-shielded Flux-Core there's a flux on the inside of the wire, but there's also a shielding gas that we use on the outside of the wire. So it's kind of dual shielded. We use two different methods to protect our weld puddle and our solidifying weld metal from atmospheric contamination. So we've got self-shielded on the right here, where we've got just the shielding is produced by the flux on the inside of the wire. And then on the left-hand side, we've got we're supplying a shielding gas, usually an argon or a CO2 or an argon CO2 mixture, to the weld puddle, and then we've got a flux on the inside of the wire in addition to the gas on the outside. FCAW equipment, Flux-Cored arc welding equipment, it's basically the same as gas metal arc welding equipment. You might need to tweak a couple of different things depending on what you got going on. But for the most part, it's the same equipment, same wire feeder. You're probably going to have to get different drive rolls, and you might have to get a different gun depending on what you've got going on, what the situation is. But for the most part, you can run one. If you can run gas metal arc welding through the equipment, you can run Flux-Cored arc welding wire through the equipment. So you can see they're very similar. Cell-shielded Flux-Cored electrodes. With cell-shielded Flux-Cored arc welding electrodes, the heat of the arc causes decomposition and some vaporization of the electrode's flux core, which partially protects the molten metal. Flux ingredients introduce deoxidizing and denitriting agents. Cell-shielded flux core is ideal for many types of field welding, especially under windy conditions. The gas-shielded process may require the use of tents or other physical shields to protect the gas shielding from winds over about 5 miles per hour. The cell-shielded process is more portable since it requires only a wire feeder and constant voltage power source. Gas tanks, regulators, and hoses are unnecessary. This simplicity extends to the torch head, which allows the operator greater visibility of the work. Okay, so to really understand what the difference is between gas metal arc welding and Flux-Cored arc welding, you can see here we've got the two processes up in the top, but if you look at our little pictures down here, the one on the left, there's no flux in gas metal arc welding. You're basically welding with a coat hanger. And I'm sure metallurgists and the people that make filler wire, if they, God forbid, if they are listening to this, they're probably throwing a freak attack. But basically, you're welding with a coat hanger. It's been processed and stretched out into a wire that you can use, but it's basically a mild steel coat hanger. That's what you're welding with. There's nothing on the inside of it. Whereas Flux-Cored arc welding, you have it's a wire, but on the inside is a flux. There's a powdered flux on the inside of it. So when it melts, when the metal melts, that flux on the inside combusts and decomposes and breaks down and kicks off a slag that covers our weld puddle, and it also kicks off some gases that will protect the weld metal from oxygen and nitrogen, which are in the atmosphere. Atmospheric contamination, which, like I said multiple times, that's what we're trying to avoid. So that's the big difference between the two welding processes, gas metal arc welding and Flux-Cored arc welding. One uses a hard wire and one uses a wire that's got a flux, a granular flux in the middle of the wire, a powder on the inside of the wire. And to contrast and compare while we're talking about Flux-Cored arc welding, Flux-Core is basically shielded metal arc welding turned inside out. Shielded metal arc welding, stick welding, has the flux on the outside. It's glued to the coat hanger. It's glued to the wire so that it'll break down and decompose when we're welding. Flux-Cored arc welding has the core, the powdered flux on the inside of the wire, the inside of the electrode. So it allows us to spool it up and make a wire out of it so we can run it for significant periods of time. Whereas with shielded metal arc welding, stick welding, when we burn our rod down, we have to stop, clean everything up, and start over. So I just wanted to compare and contrast filler metals here and why, some of the major differences, which kind of gets back to the processes and what's the difference between the processes. Manufacturing of Flux-Cored electrodes. So just to beat a dead horse here, so we start out with a flat piece of steel or whatever metal we're going to make the electrode out of, and it's like rolling your own cigarette, or use whatever analogy you want, but we just put a powder in there, crimp it down, and then they spool it up on a wire. Or in a roll. So that's how we make Flux-Cored arc welding electrodes. Here you can see the core in the middle is a granular powdered substance, and then it's got a metal sheath on the outside of it. You can get this stuff in stainless steels, all kinds of different alloys of carbon steels. There's a lot of different variations for these weld filler materials. Flux-Cored arc welding advantages. You got higher deposition rates. You're using a spool of wire, so you can really just pour the coals to this and go. You don't have to stop and change electrodes, and it's you can use a lot. You can just lay down a hell of a lot more metal. It's got deeper penetration than shielded metal arc welding. You can put down high quality welds. It can be done X-ray quality depending on the situation. Less pre-cleaning than gas metal arc welding. That flux a lot of times is going to let you weld over, small amounts of rust or maybe mill scale or something that would mess up another process. Slag covering helps with larger out of position welds. So a lot of this stuff you can weld with out of position. And the self-shielded Flux-Core is draft tolerant. So if you're just using the self-shielded Flux-Cored arc welding electrodes, you can be out in the middle of a windstorm, and there's some parameters on that. You can't be in a gale, 50-mile-an-hour winds, but you can be welding in a windier situation than you could get away with if you were using gas metal arc welding or the dual shielded or the gas shielded Flux-Cored arc welding. So one of the disadvantages here is slag removal. You're going to have to remove slag when you're Flux-Cored arc welding. Some of the slags, depending on the manufacturer and the type of electrode, it'll remove the slag will just peel right up. Other times you're going to have to fight and chip, and it's just some nasty stuff to remove. Just depends on the formulation, how the machines are set. There's a lot of different variables, but you're going to be removing slag. This can be a pain in the neck, depending on what you got going on. Flux-Cored arc welding limitations. Like I said in the previous slide, you got to remove the slag. It's more smoke and fumes than gas metal arc welding or gas tungsten arc welding. You can have a lot of splatter depending on which electrodes you're using and what the situation is. The wire is more expensive because you have to put that flux in there. Whereas gas metal arc welding wire is basically just, like I said, it's just a coat hanger and they neck it down. They just put it to, 035 or 045 or the size that you need. So Flux-Cored wire is a little more expensive than gas metal arc welding consumable electrodes. Equipment is more expensive and complex than for shielded metal arc welding. So because you got guns, you got wire feeders, you got a whole bunch of different stuff for this process, different equipment as opposed to just some cables and go. This process, the equipment's a little more expensive than it would be for shielded metal arc welding. The plasma arc cutting process. The plasma arc cutting process uses high temperature, high velocity jet of gas exiting from a constricting orifice of the torch tip to melt a localized area and removes the molten material by force of the plasma jet. The force of the arc pushes the molten metal through the workpiece and severs the material. So here you can see a plasma torch gun and how the process works. You're just heating this stuff up and punching a hole through the material and blasting it out of there with the gas. Plasma arc cutting process. Plasma cutters work by electrically charging a gas within a plenum, a chamber that surrounds the electrode. This charge superheats and ionizes the gas, which is now a greatly expanded in volume and pressure plasma gas. The electrically charged plasma then exits the torch nozzle through a constricting orifice and arcs to the surface of the grounded workpiece, creating a stream of directed plasma approximately 30,000 degrees Fahrenheit, moving at approximately 20,000 feet per second, reducing metal to molten slag. The plasma itself conducts electrical current. The cycle of creating the arc is continuous as long as the power is supplied to the electrode and the plasma stays in contact with the grounded metal being cut.
Air carbon arc gouging. Air carbon arc gouging is a process of gouging metal by heating it to a molten state and then using compressed air to blow away the molten metal. The equipment consists of a special holder that uses a carbon or graphite electrode and compressed air fed through jets built into the electrode holder. A push button or handheld valve on the electrode holder controls the air jet. So yeah, it's not a complex process. You're just putting a lot of amperage into this carbon or graphite electrode that's usually covered with copper. You're creating a pool of liquid metal, and this blast of compressed air is just blowing that metal out the other side. So if you've ever been in a shop where they're doing a lot of carbon arc gouging, you'll know that you've been somewhere where they're doing carbon arc gouging. It is very distinct, very loud. I used to work in a foundry back in the day, and they used this process, and you had guys that had been doing this for years, and they were like artists with this process. They could chop out welds or dig down into a defect in a casting and find a defect, and then they'd re-weld it back up. But yeah, they would blow liquid metal all over. I mean, they were in their booths, of course, but it was a very noisy and I think terrifying for the people that hadn't been around it. You'd have people going on a shop tour or a foundry tour, and they're going through there, and the sound was just horrific, jet engine levels of sound as they're blasting that liquid metal out the other side of what they're trying to remove it from. So, but yeah, that's air carbon arc gouging. Okay, we're going to talk about air carbon arc gouging. Air carbon arc gouging is pretty good way to go as far as I'm concerned if you need to chop something apart or really move a lot of metal. Just a little precursor before we get into the slides with pictures and words and whatnot. Air carbon arc gouging is basically a carbon rod, and it's covered with copper, and the copper helps the electricity flow. And you run a bunch of amperage through this thing. You touch it to the metal, completing the circuit, and you've got some air blowing behind it, and it'll move metal as fast as you can touch it down and keep it going. All right, here's the pretty standard setup for carbon arc gouging. On the left, you can see you've got the holder, and it's pretty similar, in makeup to a shielded metal arc welding electrode holder. The only difference here is you've got compressed air coming in. So when you can see the electrodes, they're all, carbon and covered in copper, and they come in various shapes and sizes. You can get flat ones, pointed ones, whatever, little circular ones, various sizes, depending on what you need to do and how much metal you want to move. Well, once you touch, as you can see the guy in the picture, he's touched that down. He's created an arc, and then he's got the air blowing. And you can see that the liquid metal that he's created from touching the weld pool, it's getting blasted out this other side. That's what you're doing with this process, is you're creating a pool of liquid metal, and you're hitting it with that air, the liquefied compressed air, and it just blasts that material out the other side. So if you've got mistakes, or you need to prep a weld joint, or you need to chop a riser off of a casting, carbon arc gouging is one of the processes that can really move a lot of metal. You can also create a mess if you've got people that you don't know what they're doing, but this is a really good process for removing defects or sculpting something or trying to remove metal. Taking metal out of where you don't want it is what this process is good for. Here's the basic setup. As you can see from the diagram, it's pretty similar to shielded metal arc welding. You got a power source, pretty much the same power source, except if you're going to do a lot of air carbon arc gouging, you use way more electricity, way more power than you would with shielded metal arc welding. The foundry, I think we used 500 amps. Maybe we used 1,000 amp machines. But that was pretty much what we used. And if you're gonna weld with, shielded metal arc welding, depending on what you're doing, your 100, 200, 300 amps is about where you're running, depending on the size of the electrode. Maybe you get up into 400 amps with a 1/4 inch diameter electrode. But this, you're talking, depending on what you're doing, you might have 1 or 2 power sources hooked together so you can get enough amperage and just really go to town. But the basic theory is the same. The only difference from shielded metal arc welding is you've got compressed air, which is used to blast out the liquefied metal. As opposed to shielded metal arc welding, you want the metal to stay there. This, you're using compressed air to get the liquefied metal out where you don't want it. You're trying to dig a hole or excavate a weld joint or excavate an area for a defect repair. This is an absolutely wonderful process to get that accomplished. Here's a diagram and a picture. Here's a weld joint to the left where you can see where they've gone in and hacked out the excavated some material. I don't know if it was originally a weld joint or not, but you can see that they've excavated a groove there using this process. So you've got the handheld electrode holder, the carbon arc electrode, the direction of travel. You can see the airstream is coming in from the back and it's blasting the liquid metal out the direction you're traveling. And it's, like I said, in theory, it's pretty much the same as shielded metal arc welding. As far as the circuit goes, you don't have a flux here or any of that because you don't want the metal to stay there. You're getting the metal out. But the basic gist of it is you're using a lot of electricity to make a pool of liquid metal, and then you're hitting it with an airstream to knock it out of there. Send it down the road, and you can excavate a groove or a hole or whatever you need to do.
Because we want to keep our not friends, oxygen and nitrogen, out of the weld pool, for some welding processes we need to supply an inert gas. We need to supply a shielding gas to keep those other gases out of our weld puddle. So a lot of times we'll use argon or helium, and sometimes, depending on the welding process and the situation, we'll use a CO2, carbon dioxide, to keep oxygen and nitrogen out of the weld pool. So that's when we use the term shielding gas. These are gases that we use to shield our weld puddle, and sometimes our weld metal, our solidified weld metal, from atmospheric contamination, which may be entering the weld puddle. Shielding gas affects the following. It protects the weld from atmospheric contamination. As I said before, first slide, oxygen is not our friend. Our main goal in arc welding is to protect the weld puddle from atmospheric contamination. That is job one. It stabilizes the arc, the welding arc. It defines the metal transfer mode along with the welding parameters. It controls weld geometry. It controls weld composition and properties, arc characteristics, penetration, speed of welding, cleaning action, and weld metal mechanical properties. This is probably a little above what we're trying to cover right now, but I threw this slide in there to tell you that shielding gas affects a hell of a lot of things in welding, and you might not need to be cognizant of it or understand it all right now, but you need to know that it exists, that there's a reason for all these different shielding gases, and it's not just at random. So there's a lot of different considerations that go into picking a shielding gas or why we use a certain shielding gas in certain situations. There's a lot of different shielding gases that we can use in welding, whether we're doing gas metal arc welding, Flux-Cored arc welding, or gas tungsten arc welding. The big ones are going to be argon, carbon dioxide, helium, and then mixtures of them all. Not mixtures of them all, but various mixtures of the different gases. Depending on what metal you're welding, which process you're using, there's a lot of different variables. We could do, half a dozen conversations or YouTube videos talking about typical shielding gases for, gas metal arc welding, gas tungsten arc welding, and Flux-Cored arc welding. But these are the typical shielding gases that we utilize when we're welding. Argon is used on non-ferrous base metals such as aluminum, nickel, copper, magnesium alloys, and reactive metals such as zirconium and titanium. Argon provides excellent arc welding stability, penetration, and bead profiles on these base metals. When welding ferrous base metals, think irons and steels, argon is usually mixed with other gases such as oxygen, helium, carbon dioxide, or hydrogen. Depending on what you're welding, you can have all kinds of mixtures of different gases. The gas you use to MIG weld or gas metal arc weld, a certain type of stainless steel might not be the exact same shielding gas you're going to use for gas metal arc welding, MIG welding of carbon steels, and vice versa. There's a whole art form and science to these shielding gases without getting into it too crazy. Carbon dioxide, CO2, is a reactive gas. It dissociates into carbon monoxide and free oxygen in the heat of the arc. Oxygen then combines with the elements, transferring across the arc to form oxides from the weld pool in the form of slag and scale, generating a great deal of smoke and fumes. Although CO2 is an active gas and produces an oxidizing effect, sound welds can be consistently achieved with pure CO2. This is generally in gas metal arc welding. Carbon dioxide is often used in its pure form with welding of carbon steel because it is cheap, readily available, and produces good welds. Summary. Okay, in this one we covered shielded metal arc welding, which is basic stick welding. We've got a piece of wire covered with, either a mineral coating or a bunch of wood chips and paper. There's various formulations of the flux that we can use on the outside of the shielded metal arc welding electrode. And I'm kind of breaking it down into terms a guy can digest. We talked about gas tungsten arc welding, where we use a piece of tungsten to conduct the electricity, and then we add the filler metal by itself. We generally hand feed it into the weld puddle. We talked about gas metal arc welding and Flux-Cored arc welding, which are more or less the same process, other than we use a little different electrode. One's got a cord electrode. It's got a powdered granular flux on the inside of the electrode, and the other one uses a solid wire, which would be gas metal arc welding. We talked about plasma cutting, plasma arc cutting. We did a brief flyby on air carbon arc gouging, and then we talked about shielding gas for welding processes. For most of my material that I throw out on YouTube, my starting point is some Nuclear Regulatory Commission, slideshows, introduction to welding technology and code courses. I use some CAN-TEACH public domain educational reference library on CANDU's technology. It's the Canadian deuterium nuclear people. Also use U.S. Army TM 9237 welding theory and application. Also use some hull technician, United States Navy hull technician correspondence course, Boilermaker 1 in Chief. Also used BT 3 and 2, Boiler Technician 3 and 2. So if what I'm trying to talk about, also Steel Worker 3 and 2, it's a CB, U.S. Navy manual. So if what I'm talking about doesn't exactly match up with, if you're trying to follow along in the Boilermaker or NCCR trainee guide, my stuff is not going to dial in exactly with what's in the printed form in that book, but it's because I went to other sources and got that information. So everything should be pretty accurate, but I just independent unit using material that's in the public domain to make my slides. All right, thanks. My name's Gary Pace. I'm a PE CWI out of Katy, Texas. If you want to track me down, there's how you can find me. You got any questions, comments, like the video, didn't like it, maybe you got a suggestion for another video, let me know. Thanks. Take care. GP out.